I don't, I'm going to have to make a remark about that.
Well, good evening and welcome to Monday Night Calculus. Really excited to be joining you once again. My name is Curtis Brown and I am joined by Steve Kokoska and Tom Dick. Really excited for the content this evening, looking at the difference quotient and a myriad of applications of that. Also, just a couple of housekeeping things before we get started. Teachers, just know that tomorrow morning I'll be posting the solutions document up here ready for your use there. And then students, if you've got questions as you are logged in, please feel free to reach out. There's plenty of teachers on the call, as well as I will pass those questions over to Steve and Tom, and we'd certainly be happy to answer those as we go through. Teachers, if you look at the very end of this session, I will make sure to post my email address where you can reach out to me for teacher professional development hours. And so without further ado, I will turn it over to Steve. I think you can take it away.
Thank you very much, Curtis. Great to be with you and Tom again tonight. Well, we're going to talk about difference quotients tonight and how they might be used to approximate derivatives. I'm going to do a couple of analytic problems. I'm going to start out actually by trying to visualize a difference quotient. I'm going to do a couple of problems that involve some interpretations. And we've got some great, I think, overtime problems today, Curtis. I sincerely hope that you've done your homework. We have some good questions for you. So the first problem tonight that we posted had to do with this. It says, explain why the following equations for the slope of the tangent line to the graph of f at x equal a are equivalent. Now, when I teach this, when I introduce the derivative or the need for a limit actually, and then eventually a derivative, I usually talk about the tangent line and the velocity problem. And both of those problems lead me to one of these two expressions. Now, I have to confess that I usually get to this one first. And I don't know why, Curtis. To me, for whatever reason, that just seems to be a more natural expression or an easier one for my students to understand. And so what I'd like to do is to look at these two expressions sort of graphically and see why they are equivalent. Now, if you look down to the bottom here, I have a couple of graphs on my screen. If you look down at the bottom left, let's take a look at this first one. And I hope that the color is showing up there. It's a little fine line there, but I think you can see I have a curve that's actually in blue. And I'm starting over here at a point A, f of A on that point. And I want to find the equation of that tangent line that's in sort of red or maroon. And in order for me to do that, I have a point on the curve, but I need a slope. But in order to get a slope, I need 2 points. So how do I do this? It's sort of a natural way to do this, to approximate it. And that is by looking at a secant line, a line that intersects this curve, y equal f of x, in A, f of A, and another point just a little bit of ways away from A. And traditionally, I tend to draw this to the right. But, we have to remind students that this is from both sides. H could be negative. I'm going to sneak in a little bit here, Curtis, if I can. In this case, I'm thinking of H as being greater than 0. So I'm a little bit to the right of A. But I could draw an equivalent sort of graph if I think about H being negative and go to the left of A. All right, if I've drawn this well enough, I know how to find the equation of that secant line. That's just the rise over the run for the slope. So let's see. If I do that, that's just f of A plus H minus f of A divided by the run here, A plus H minus A. And that's exactly this expression right here. And by looking at my graph, I think I can convince my students that as this gets closer, this point gets closer and closer to A, as H gets smaller and smaller, as this point moves down the graph, the secant line gets closer and closer to the tangent line. And it seems reasonable that this slope should get closer and closer to the slope of the tangent line. So that's one way that I introduce this idea of a need for a difference quotient and this need to somehow evaluate that limit. Now, another way to look at this visually is just using different notation. I'm still going to start over here at A and f of A, but this time I'm going to move to the right of A just a little bit. I'm going to call that value X. The point up here on the line would be X f of X. And what's the slope of that secant line this time? Well, it's just the change in Y, f of X, minus f of A, divided by the change in x minus a, and there's another expression for the slope of that secant line. How do I find the slope of the tangent line? Well, I let x get closer and closer to a, expressed by this limit, and that's another way to think about, well, the need to evaluate that type of limit. Now, I think you can see, Curtis, that those two expressions, they're equivalent. I think we've talked about this before, but I often think about this as the alternate definition of the derivative, although some people find that easier to work with first, and that's fine. But there's also a way to go from this expression to this one if you want to think about this analytically. And we could do that just by saying, well, let's let x be equal to a plus h in this expression right here. Well, what happens to this expression as h goes to 0? As h goes to 0, well, that's equivalent to saying, well, x is going to a. And hence, if we make all the substitutions, these two limits right here, this one and this one, are indeed equivalent. So I think that's a good problem to sort of start out with when we talk about difference quotients. It emphasizes, I think, the need to evaluate limits of this form. It introduces students to these two sort of definitions of the derivative when we get there. I like that. The second problem for today was a couple of analytic problems. And Curtis, I still feel that there's a need to do some of these problems. That is, simplify the difference quotient, and maybe, although I didn't do this in some of these problems formally, I will take a look at some of them. Evaluate the limit as h goes to 0 or as x goes to a. And in fact, you and I know that in the AP pre-calculus syllabus, or CED, they talk a lot about difference quotients. And so this should be a common problem in that class. So let's take a look at a couple of common types of problems that I think give my students some good problem-solving techniques. So let's look at f of x equal x cubed. And all I want to do here is to take a look at this difference quotient and try to simplify that as much as possible. Now, it's not very mathematical, but when I start out with the difference quotient, I frequently tell my students, what do you mean by simplifying? Well, what I'd really like to do is to somehow get rid of that h in the denominator. That lonely h in the denominator, which is tied to, as h goes to 0, I want to somehow get rid of that 0 in the denominator, that h in the denominator. So, okay, the very first thing I need to do here is to evaluate f at a plus h. And just as an aside, Curtis, I find that a lot of my students have difficulty just evaluating functions at different values. How do you evaluate this function at a plus h? There's still a lot of confusion about that. And one of the emphasis in AP pre-calculus, we hear this theme throughout, is that of functions. How do you evaluate functions? How do you evaluate them at different sort of expressions? So all right, f of a plus h is a plus h cubed, minus f of a is a cubed. And so the natural thing to do here is to sort of expand this out. Now, I did that kind of quickly there, but I'm going to ask you a quick question, Curtis. Here, there's some math that's good for the soul here, I think. I'm going to look at the coefficients on that expression, and they are 1, 3, 3, 1. Do you remember where those coefficients come from and how we get them really quickly?
They look like an expansion. What's his name? Pascal.
Oh, what's his name?
Had something to do with that,
Very
huh?
good. So the line above this would be 1, 2, 1, okay, and 1, 1. What's the line below this? Remember that? 1, 4, 6, 4, 1. How do you get those? By adding the two numbers
Right.
above it like that. Remember
Yep.
that? But is there another way to get this 6? Do you remember how to get that, Curtis? Remember that?
Probably not tonight.
No. All right. Well, we'll put that out there. Well, ask.
Hey, Crystal gave me the Pascal's triangle, which was great.
Oh, very good.
So,
Very good. Geez, they know that even in Canada. Huh? How about that?
yeah.
Wow. Well, how do you get that 6, Curtis? Do you remember?
I'm waiting on somebody in the chat,
Somebody to help
honestly.
you? Okay. All right. Well, we'll leave that out there.
Well, you get me Pascal's triangle and then combinations, but I mean that's the same
Good. Very
concept, right? 4 things taken 2 at a time. Yeah.
combinations. Very good.
I was trying to think of another way to come up with it, but to me, all those seem to run together.
Okay. All right. So good problem solving techniques. I've expanded out that expression and some good things happen here. The A cubes cancel. And as I stare at that expression long enough, I see that each of those terms or remaining terms has an H in it. And H is part of a product. And so I can factor that H out and some really good things cancel here. Happen. The H's cancel. And for me, non-mathematically, I've gotten rid of that H in the denominator and I'm left with this expression, and that's a good thing for now. We'll leave that problem as it is. I like that. Here's another one. Suppose we take a look at f of x equal 1 divided by x, and this time I'm going to use that alternate expression for a difference quotient, or that expression that's in my alternate definition of the derivative. So f of x minus a, and when I tell my student divided by x minus a, I tell my students here is, well, what I really need to do is I want to somehow work to simplify this to get rid of the x minus a term in the denominator. So let's see what happens. F of x minus f of a, 1 over x minus 1 over a. And good problem solving technique here. I think the natural thing to do is to try to get a common denominator in the numerator. That sounds kind of weird, but common denominator in the numerator. Now, if I've done all of that correctly, I'm going to leave that numerator alone. I'm going to take the reciprocal of the denominator and multiply. And I can see some good things about to happen. I wrote out a couple of extra steps maybe here. I factored out a minus 1 out of each of those terms so that these two terms would cancel very nicely. And I'm left with minus 1 divided by a minus x. And yep, the x minus a term is gone in the denominator. And I have a question for you. Curtis, I'm going to take the limit as x goes to a of this expression, minus 1 divided by ax. How do I take that limit, and what's the answer there?
Well, it should approach x to 1 over x squared, right? Or a, yeah, 1 over a squared, I guess.
There you go. So it should be minus 1 over a squared. In fact, direct substitution works here.
Mm-hmm.
So direct substitution works. There's no division by 0 at all. In fact, we can make an argument about continuity, and direct substitution works here because this is a very nice rational expression, and we can make this direct substitution. Okay, the AP Calculus exam right now, the course is big on interpretation. So, okay, how would you interpret this expression? We're making a little bit of a leap of faith here, but how would you interpret that expression in the context of this function? What is that minus 1 over a squared? What would that be? Can you give me an interpretation of that expression? What would that be?
Watching the chat.
Deathly silence here. What would that be?
Come on, chat. Come on, Tom.
Somebody.
Slope of the line at x equals a.
Slope of the tangent line. Very
Slope
good.
Of the tangent line at x
Slope
equals
of the
a.
tangent
Thanks,
line
Wanda.
for the curve. Y equal 1 over x at x equal a. Very good. Excellent. Beautiful. All right. Well, let's try one more of these, and then I'll let Tom do a little bit of technology. One more with another, I think, good problem-solving technique here. Boy, there's a lot on this page. This time I've got f of x equal to a rational expression, x plus 2 divided by x plus 4. I'm going to go back to my first sort of difference quotient that I would arrive at, again, by looking at the tangent line problem or the velocity problem. And I'm going to try to simplify this difference quotient with the same goal in mind. That is, trying to get rid of that h in the denominator. Okay. Don't let me make a mistake on this one, Curtis. I'm going to evaluate f at a plus h. And I think I did that correctly. A plus h plus 2 divided by a plus h plus 4. I'm going to subtract off f of a, and there's the lonely h in the denominator. And I think, good calculus vision here, the natural thing to do is to, again, get a common denominator in the numerator. This one's a little bit longer, but not that bad. So the common denominator is the product of these two denominators. And so, okay, I'll spare you a little bit of this. I did all the multiplying out, and here's what I have. Holy Toledo, that looks awful. But again, I think some really good things happen here. Don't let me miss any. The a squareds cancel. There's a minus sign out in front there. What else happens here? The 8's go. Hey, the a times h goes. Let's see, did I do this right? Yeah, 2a plus 4a. 2a plus 4a.
Need a 2h. Yeah.
Right? And I've got a 4h, and this is going to be a minus 2h.
Yeah.
And so I'm left with a 2h in the numerator, the product down there in the denominator, and I still have to multiply by the reciprocal, but boy, some good things happen here. The h's cancel, and I'm left with this expression without the h in the denominator, and I feel obligated to do one more step here to take a look at the limit as h goes to 0 of this expression. So this is a plus 4. See, what is that? A plus h plus 4. And what happens to that expression, Curtis, as h goes to 0? What am I left with?
2 over a plus 4 quantity squared. It looks
Beautiful.
like.
2 over a plus h quantity squared. Excellent.
Oh,
Yeah,
H.
beautiful.
Yeah.
But h, I beg your pardon. 4.
That should be a 4, right?
Should be a 4. That's
Okay.
a 4. And the interpretation here is exactly the same as before. We can interpret that as the slope of the tangent line to the graph of this function at the point where x is equal to a. That's terrific. That's great. Okay, I'm going to turn it over to Tom for a little bit of technology. I'm going to come back and do a couple of applied problems and maybe even talk a little bit about a couple of scoring techniques or scoring tips for the exam. Okay, Tom, all yours.
All right, sounds good. So let's see. I'll share my screen here. Let's see if this works out. So hopefully you're seeing my TI-84.
We are indeed. Looks good.
Fantastic. Okay. So I'm just going to take off on one of Steve's examples and just investigate this a bit on the TI-84 using graphics. So I'm going to go to the y equals menu here and go ahead and enter that first function that Steve was looking at on number 2. I think it was just x cubed.
Right.
All right, great. And I'll tell you what, let's just go ahead and graph that. I'm going to use zoom. And not to zoom in on it or anything right away, but just to pick up one of these standard windows. I'll go to my usual favorite here. It's a zoom decimal where our pixels are going to be worth 0.1 in both directions. And the hash marks on the axes are going to be nice integer values, of course. That looks like x cubed. And let me just, I'm going to trace over to point. Why don't I trace over to x equal 1? Okay. And the point I wanted to make here was the difference quotient. What we're doing is we're looking at the difference in the y values for the function over the difference in the x values for 2 points that are close together. So let's suppose I was wanting to approximate the slope of the tangent line right here at this point. So this is the point 1, 1 on the graph of y equals x cubed. Well, one of the points I'll use is this point here. And now I need a point close by that's on the graph of the function. So what I'm going to do is I'm just going to trace 1 pixel over. Take a look at what I get here. So now I'm at x equal 1.1. Hey, look at that y value. That looks like a line out of Pascal's triangle. If you,
How do you like that?
this is
Wow.
not a coincidence. I'll let you try to think about that. So, how is the y value? We take the 1.1 and cube it, or you can think of 1.1 as being 1 plus 0.1.
Right.
Expand it out, and you'll get 1.331. And I like to impress on my students, just using those two values, what would it be your approximation for the slope? Well, we would take the difference in our y values. Well, that would be, let's see, both the x and the y were 1 where we started. So the difference in the y values is going to be that 0.331. The difference in the x values will be 0.1. So I think we'll end up with about 3.31. Okay. So that's a really rough estimate for the value of the slope of the tangent line there. Now let me go ahead and back up to 1, 1 again and just zoom in at that point. So I'm going to do a zoom in. And we're right there at 1, 1. So let me zoom in. All right. And let me zoom in another time. Oh, that's already looking pretty straight. And let me just do that game again. Let me just trace over just 1 pixel over it. Now that's going to be a point much, much closer to my original point 1, 1. So let's trace over 1 pixel.
To the right, you mean?
Oh, excuse me. You know what I did is I forgot to turn on the trace. There we go. So I actually got off of the graph. Okay, now let's trace over 1 pixel. There we go. And if you'll notice, okay, much did x change? Well, it's this 0.00625. That's how much above 1 we've moved to the right. So let's just think about that 0.006. And the y value changed by 0.0188. Okay. And you can see that this is roughly a change about 3 times as great as the change in x. Kind of rough, but it's actually closer to 3 than the value we got before. And if we kept zooming in, we'd get closer and closer to this limiting slope of 3.
Hey, Tom,
Yes, Curtis.
you want to do something cool?
Oh, surely I would love to. Go ahead.
Leave your cursor where it is right now and jump over to the home screen.
Okay, so just do a quit.
Yeah. And you were doing f at 1, 1, right? Or f at 1, right?
Right.
So can you make a fraction for me, like alpha
Sure.
xt theta n?
Okay.
And
Oh,
get
sorry, I'm
yourself-
just entering this as one expression over another. Or?
Oh, sure. Yeah, that's
Okay.
fine. That's fine. So the difference in the y's, so you could do y minus 1.
So just do an alpha y.
Yeah, do alpha y.
And the last value that was in y.
Will be stored in y.
Yeah.
Minus 1.
Which was our starting y value.
That was your starting y value. And then divided by the same expression, alpha x. You need the divide. There you go.
Yeah, there we go. The x minus 1, that's going to be the latest value of x,
Uh-huh.
which were the ones that we saw on the trace screen just a little
Yep.
while ago.
Yep.
Yep.
And now if you hit enter, you should be able to get that.
So there's that 3.01, much closer to 3. Yeah.
And you could continue to play with that on the, either the trace screen and zooming in or even in the table.
Yeah. So very good. Yeah, this is very nice. So that's a quick way to do a more exact calculation, more precise calculation on the calculator screen. And the big point here is the language of limits we're approaching as x approaches a. Graphically, that's zooming in on where x equals a, comma f of a, and then just picking that point and a point close by on that zoomed in picture. It gets across to the same thing. Now I'm going to go stay with this for a bit. Let me go to the y equals menu. And what I'd like to do is think about, what if we repeated this process? This was looking at that process of the difference quotient at x equal 1. Or if you're thinking in terms of the a value, the a was 1. So was the specific point of interest. But let's suppose we tried to repeat that at lots and lots of points, computer difference quotients. So what I'm getting at here is we've got y1 is x cubed. What if we took, let me pull out y1 from the y variables. So I'm going to evaluate y1 at x,
right?
Plus 0.1. What I'm doing is I'm at an x value, and I'm imagining moving 0.1 to the right. And then I'm going to subtract y1 of x. And then I'm going to divide by the change in x. Well, x plus 0.1 and x, the difference between those is just 0.1. So I'll just be dividing by 0.1. Okay. Now, what I'm interested in now is actually graphing this difference quotient function. This is a new function defined in terms of our original function y1 is x cubed. And I'm just curious, what does that function look like, this difference quotient function? So I'm going to go ahead and back to my original Zoom decimal window here. And let's take a look at the graph of x cubed. There it is. And now we should see the graph of the difference quotient function. Oh my gosh, that looks like a familiar function, doesn't it? Let's see. And in fact, what this, at each point on my original graph, the blue graph, at the corresponding x value, the red function graph is going to be an approximation of the slope of that. So down here at the vertex, okay, where my cubic is very, very flat, getting a slope of 0. That's the y value on the red graph. If I traced over to 1, oops, overshot. There we go. Okay, there's 1, 1 on the blue graph. That's my y equal x cubed graph. Now let me hit the up arrow to switch over to the red graph. This is an approximation of the slope at that point.
Yeah, pretty good.
And the shape of it, we really get a sense of a shape of the derivative graph. And in fact, this is a great skill for students to pick up, is just sketching a graph of a derivative, just given a graph of a function. I'll tell you what's super cool about doing it this way is if I go back to my y equals menu, this y2, that's my difference quotient function for y1. Notice it's in terms of y1, which means if I change my y1, this thing's ready to go again. It's all set up, good to go. So for example, I could even try something like, how about sine of x? Get rid of that. Well, let's see. Okay, we'll try it again. Okay, so sine of x. So that's my new y1. And now when I graph this, it's going to graph y equals sine x, but it's also going to graph this really strange function. It's sine of x plus 0.1 minus the sine of x divided by 0.1. And well, let's just take a look at what that looks like. Here comes my sine x graph. And then here's the difference quotient graph.
It's pretty cool how closely.
Yeah, I was
Well,
frankly
even with just the
amazed how
0.1.
much this looks like. I mean, even my students look at this and say, that looks like cosines.
Even
I
I
think
look
they
at that and
do.
say that looks an awful lot like
It
cosine.
does, it does. In
I
fact,
have-
it makes you curious. Oh, I'm sorry, Steve, go ahead.
I have one. Would you try one for me?
Sure. If it's
Would-
okay, I'm going to just do one more thing with this
Sure.
one, then you can try
Sure.
yours.
Okay.
I'm just curious how the cosine graph compares with this difference
Oh,
quotient.
there you go.
So I'm
That's a
going to
good
put in the
idea.
cosine of x.
Yeah, that's a natural thing to do, is to say, hey,
Yeah. So how
this
close
is-
was it? It sure looks really close.
Yep.
And now we'll graph all three of them.
Boy, that's pretty close.
It's pretty close. And what I would say here is the fact that you can see any red at all tells us they're not exactly the same. If
Mhm.
those graphs were identical, the black graph would have covered the red graph exactly. But we can see just a little bit of different. But I was flabbergasted at how close it was, because the difference I'm using, the 0.1, that's not that small. So
That's really not that small.
Yeah, when
Yeah.
we think about zooming in or taking a limit, we're getting closer and close. We're getting super close, right? We're talking about really small differences. But even a moderately small difference gives us a pretty neat value. Okay, Steve, you had
Just
one
try
in
one for me. I'm sorry, Tom, you piqued my
Sure.
interest a little bit. In Y1, if you could, just put in e to the x. And let's see what
Okay.
that does for us, because I think
Okay.
that's a neat discovery if this works.
Okay, so we're going to put in e to the x. And our y2 is already set up. So
Ready to go?
it's
Okay.
ready to go. That's why I said it's really quick now. Let's do a graph. Well, there's our e to the x graph.
How
Oh my
about that? How about that?
That's pretty.
goodness.
That's pretty
And-
slick.
And this skill of sketching the graph of a derivative directly off the graph. If I was just given this graph of y equal to e to the x and somebody didn't tell me that it was e to the x, so I was just trying to graph it based on the characteristics. Well, let's see. It looks like the slope's always positive, but it's really, really flat over here. So the slope graph, or the difference quotient graph, should be really close to 0. And then as this graph climbs, the slope is climbing too. And so it makes sense that the slope graph would look similar to the original graph. What's amazing here is just for this particular base, man, it's really close match.
Yeah.
I don't even have to bother with the Y3 on this one, Steve, right?
Yeah.
We've already got it. But anyways, I find this is a fascinating thing to do. And folks should realize on the 84, when you do a numerical derivative, it's actually taking a couple of these difference quotients and averaging them. It's doing one to the right, one to the left, and averages the two. This is sometimes called the symmetric difference quotient. And it's an extremely nice approximation to the derivative graph. Where that's found is when you go to the math menu. It's that number 8, n deriv. And I think it uses something like 1/1,000,000th as the difference value on either side of the X value that is the point of interest. All right, Steve, I think I will turn it back to you unless, Curtis, you noticed anything that I should try to respond to before I turn it back over to Steve.
Nope, I think that's pretty good.
Okay, so oops, let's see. I need to do a stop share. There it is. And Steve, back to you.
Fantastic. Thanks, Tom. All right, Curtis, we've got a couple of applied problems here before we get to the overtime problems. So I like this one. This has to do with a coffee house chain. There was a famous coffee house chain that started in the Northwest, wasn't there? I think that's true. So the number of locations for this coffee chain is given by a function n of t, where t is measured in years. And I've created a table here, a table of values for n of t for selected values of t from 2012 up to 2022. And the very first thing I want to do is just, well, let's find the average rate of growth from 2016 to 18 and 18 to 20. I should think a little bit about the units of measure, because on the AP Calculus exam, we're asked about units frequently now. And you might think a little bit about, well, what do these answers suggest in general about the growth of locations? Let's see if we can interpret these two values a little bit more. Well, all right, I'm really taking a look at a difference quotient to find this average rate of growth. I'm going to look at n of 2018 minus 2016, n of 2016 divided by the difference in the x's, change in the y's divided by the change in the x's. I get these values by going back up to the table, pulling these values from the table. And I think I got 860, and I believe I've done this correct. The units are locations per year. So the average rate of growth from 2016 to 2018 is 860 locations per year. And from 2018 to 2020, I did a similar sort of thing in this expression, and I came up with an 840 locations per year. So what does this all suggest? Well, since the average rate of growth is a little bit smaller in those 2 years from 18 to 20, this suggests that the growth of locations is slowing down, is decreasing a little bit. And that's about the best I can say here, the best I can do right now. Now in B, let's see if I can arrow up a little bit. Thanks to Mark Corrali, this is working a little bit nicer tonight. It says estimate the instantaneous rate of growth in 2021. Now, just as sort of an aside, I apologize for this, Curtis. I'm going to try to arrow back up a little bit so that I can get my table in here. I don't know if you'll see a question exactly like this on the AP exam anymore. I think that they would be more precise in telling you which years to use. I mean, for many of us who have been doing these problems for a long time, we would look at this table and say, oh, well, you know, 2021 is between 2020 and 2022. And so it sort of seems natural to use those 2 years to estimate this instantaneous rate of growth. And if you just think about a graph of a function and you wanted to estimate the slope of the tangent line, it seems to make sense to get as close as you can to that x value, that t value in this case of 2021. But the truth is that there are many other ways to estimate this instantaneous rate of growth. I could use, for example, 2018 and 2022. So some of us might change this question just a little bit by saying something like, give me your best estimate of the instantaneous rate of growth. And that might imply to use 2020 and 2022. In any event, I think on the free response portion of the exam anyway, it might say something like use the years 2020 and 2022 to estimate the instantaneous rate of growth. Sorry about that, Curtis. That was a long way to go for this, but here we go. I'm going to arrow up now. I'm going to form this difference quotient. Nope, if I can. Here we go. There we go. I'm going to arrow up a little bit. There's my difference quotient. I went to my table here to get those values, and it turns out to be 805 locations per year. So an interpretation of that is the instantaneous rate of growth of store locations is approximately 805 locations per year at that time. One more little thing, Curtis, before I leave this problem. If this were a question on the free response portion of the exam, you know, we often are asked about, well, for simplifying, what do we do for simplifying final numerical answers? And remember, a final numerical answer does not need to be simplified. But in my line here, in my solution line, where is that sort of cutoff point? Well, the student cannot stop right here, okay? They have to go to the table. They have to pull those values of n of t from the table. So that circled expression is not considered a final numerical expression. One other little thing in problems like this, we often require students to give us both a difference and a quotient. So what does that mean? Some of our students, many of your students are so good at this. They're looking at this very quickly. They do the subtraction in their head, and they might start out this problem by writing, well, it's 1610 divided by 2. Now, even though that's correct, they would not receive full credit for this because we need to see both a difference and a quotient. I see the quotient there, but I haven't seen any difference. So in order to get full credit for this type of problem, you've got to pull the values from the table, and we've got to see both a difference and a quotient. Beautiful. One more tabular problem. I like this one, Curtis. This is a kind of a nice applied problem. So researchers measured the concentration of a certain drug in a patient in a hospital starting 1 hour after the administration of 30 milliliters. And so once again on this table, I'm giving you selected values of C of t for certain values of t given in hours. Okay, I won't go through all of this in gory detail, but I'm asking for the average rate of change of C with respect to t over each one of these time intervals. So once again, what I've done in all 4 of these places is to form this difference quotient, go to the table and read off the appropriate values and do a little bit of simplification. Notice that these are negative. How do you interpret this? I didn't include any units here, so how do you interpret this? Well, I think the best that I can do, and Tom and I talked a little bit about this, is that the rate of change of concentration of this drug seems to be slowing down, as t increases. And that's about the best that I can do here. And I think there was a part B here. Estimate the instantaneous rate of change in the concentration at t equal 2. And I said in 3 different ways here. And the reason that I put this problem in, once again, was to emphasize this issue about, well, what estimate do you think is the best and why? So I found 3 of them here. Starting or using t equal 2 and 1.5, 2.5 and 2, and then 2.5 and 1.5. So I went a little bit to the right, a little bit to the left, and then a little bit to both the left and the right. And which one of these do you think is the best estimate? And I really don't know the answer to that. Here's a question for the chat. If we had a graph, maybe we could tell, or we might be able to answer this question. If we had a graph of C, how might we use that graph to determine which of these is the best estimate? Sort of a rhetorical question. We'll leave that one out there. Tom, did you have just a little bit more technology before I get to the overtime problems? Is that correct?
Yeah, sure, Steve.
Okay, great. Just a little bit more and we'll try to get back to those. Cool.
Okay. Good deal. All right, I'm going to go back to the 84 there. And what I'd like to do is the last couple of problems that Steve looked at, dealt with a table of values and approximating derivative by basically calculating difference quotients, drawing values out of the table. Just want to show that there is a way to work essentially with tables of values on the 84. And just want to show what that looks like. So let me quit out of this menu that I'm in. Let's clear this out. And where I'm going to go is this menu that says stat, S-T-A-T. And I'm going to go into edit. And when I do that, I get into a little editor here that has columns that are labeled L1, L2, and so forth. These are kind of dedicated list variables. They give you a list of values. In this case, the values are arranged in a column. Now, I've taken the liberty and go ahead and filled in some lists. You might recognize these numbers. L1 and L2, these were the year values, and this was the coffee house problem, number of locations. That's the L1 and L2. L3 and L4, this is the problem that Steve just looked at, where he's looking at concentrations. L4 is the concentrations, and L3 are, again, time values spaced apart by, looks like 0.5 increments.
Right.
And so let's see, in doing difference quotients, we're going to be taking differences in the Y values. I'm going to look at these last two lists here, L3 and L4. So we'll be doing differences in Y values over differences in X values. Okay. Now, the difference in the X values, this is often the case, especially, kind of time where somebody's taking readings at specific time intervals. This is kind of nice as the time data is equally spaced apart. So my delta time, delta t, if you will, is 0.5 for each successive pair of values. But the concentrations, those are varying a bit. And I'd like to do actually, I'd like to generate a list of these differences. And there's a feature we can do that quite nicely. So I'm going to go to use this last column that's visible here. It says L5. I'm going to arrow up into L5. And I'm going to define what this list of values will look like. And to do that, let's see. I'm going to go to list, which was the shift or second of stat. And it says names. Okay, there's those list names. Looks like there's 6 of them. You can also name your own lists if you want. You can see I have a few special ones there. I'm going over to operations. That's the OPS. If you look down that menu list, look at number 7. See that little delta? That's going to give us successive differences in list values for another list. So I'm going to select that one. So I'm going to make L5 be the delta list of L4, which is my concentration values. So I'll go back now to list and go down and get L4. By the way, you can find L1 through L6 down on the keyboard. You didn't have to go into this. So if you look down at 1 through 6, the second shift of those is L1 through L6. But let me do delta list of L4. And let's enter that and see if it works. Now let's do a reality check here. So the first value, notice that L5 has 1 fewer value. That's because it's like the fence post problems. Okay. So these are the differences. So my first would be like should be 0.47 minus 0.61. Does that look like it's making sense? I think it does. And then the next value should be a 0.37 minus 0.47. I can do that one in my head. That should be a negative 0.1. And so on and so forth. So you can see this is giving us exactly the values, the delta values. Now I'm going to redefine my L5 again. So I'm going to go up to L5 and clear that out. And I'm going to do the delta list again. Of L4. This time I'm going to get it right off the keyboard. So I'm doing the second shift of 4. So I'm going to do those same differences, but now I'm going to divide each one. Whoops, let's try that again. By the delta x, or delta time, I should say, which was 0.5. And now these are my approximations of my difference quotients for each pair of values. So really nice. And actually, 2 of the values Steve last looked at are right here. Let's see, from 1.5 to 2, we're going to find that in the line that goes with 1.5. That's because this difference quotient is the one from the second difference quotient is the third L4 value minus the second one. So, and then the one that's, I kind of tripped over my tongue there, I apologize, but these 2 values in the second and third line of L5 are 2 of the values Steve had.
Yep.
The third one Steve had, he talked about taking a difference quotient where he used both a value, the value corresponding to 2.5 and the value corresponding to 1.5. And then there he used the difference of 1 in the denominator. I want to point out that's also the average of these 2 values. And that will always be the case. That's a nice little algebra exercise. So this kind of list functionality is kind of handy. You can do some neat things with it. Okay, Yes, sir.
I just learned the calculator functionality tonight. That's awesome.
Oh yeah, that delta list stuff, it's really kind of cool. All right. I'll stop the share and turn it back over to you, Steve.
Alrighty, thank you, Tom. I assume when you do that delta share, that if in the list that you were using L3, that if the differences were not constant, when you defined L5, you could do delta list L4 divided by delta list L3.
Absolutely. Yep, that's exactly right. So you can even take data where both the independent and dependent variable data is not in equal increments.
Yep. Okay. Well, Curtis, there was some great overtime problems this week. These are problems that we took off of the Facebook page. A couple of them are kind of quickly here, and we might even leave a couple of problems for our participants to look at. This one was interesting to me. This was somebody asked to use technology to sketch the curve described by this equation. I don't know if Tom can do this on the 84, but we'll leave this as an open question probably for tonight. I tried to do this using Mathematica, and I found an easier way to do this, I think. My natural instinct was to use something in Mathematica called contour plot. And so I think the way that this works, and I'm not positive about this, but I think the way this works is you take a rectangle. And so I think my viewing window here, if I've got this right, is -4 to 4. I think it was -2 to 5. And I think what Mathematica does is it takes that rectangle and it takes a bunch of points in this rectangle and it tests them really quickly. How close are you to equality when you plug in that X and Y coordinate? And it came up with this curve, which isn't bad, except you'll notice that it looks a little funny over here where it's close to the Y-axis. It almost looks discontinuous there. Well, one thing I did notice when I went to plot this using contour plot is if you just think about this expression a little bit, on the left-hand side, when you take the square root of an expression, first of all, what's inside has to be positive. But the square root always returns a positive value. It's a function. It returns only one value, the positive value. And so that means what's on the right-hand side here has to be positive, and that only happens if x is greater than or equal to 0.
Mm.
So the domain here, in some sense, or the graph of this expression, must only exist for x greater than or equal to 0. So someone suggested, well, okay, let's square both sides of that expression. And when I did that, oddly enough, contour plot gave me a much better graph, but it gave me, of course, all of this part over here where x is less than 0. And so a sneakier way I found, I think, to do this was to square both sides and solve this expression. I was lucky in this case. I could solve this expression actually explicitly for y as a cube root.
Yeah.
And when I graphed that, I got a very nice expression with Mathematica. And I suspect that the 84 and of course the TI-Nspire would return a good graph there too. So that was a nice problem.
That is
Here's
a nice
another
one. Hey,
Here's
Steve,
another
real
one.
quick.
Yes, sir.
I got a question in the chat from Michelle
Okay.
about the inverse trig function derivatives that are on the AB exam.
Okay.
Just sine and tangent? Or are there others as well? And you can respond to that later if you need to, but
Well, Tom will have to help me with this, but I think students should know all 6 inverse trig functions. But of course, in finding
derivatives. Right.
antiderivatives, generally they only need to know, I think, the sine inverse, tangent inverse. Tom, have any of the others appeared that you can think of? Oh, I have a feeling that
Yeah, I'm not sure.
I have a feeling that inverse cosecant or secant appeared somewhere recently.
Yeah, I'd be surprised if at least, yeah, if the inverse secant, I would think the inverse secant would lead.
To be there.
The
Yeah.
derivative would be there. Thing is, my own class, you know, just a matter of course, to always do all 6. But yeah, as in terms of showing up on the exam, it's going to be much more likely inverse sine, inverse tangent. But I wouldn't rule out inverse secant.
Yeah. So I guess the bottom line is, Curtis, they should be exposed to all 6 of them.
Yeah.
When you get to integration, maybe just those 3 would be the most common that would appear.
Yeah,
that's
but
just-
exposure to all 6 is a good thing to do.
Absolutely. Absolutely. We're running a little late, Curtis. I won't go through this one in gory detail, but we will post this one. I've seen a couple of questions like this on the Facebook page recently. We have a piecewise defined function, and we want to find these constants, find values of these constants a and h, so that this function is both continuous and differentiable everywhere. So just kind of quickly, it is a quadratic to the left of -5. It's a quadratic to the right of -5. So it's continuous and differentiable over there. -5 is the only place we need to worry about. How do we make it continuous bluntly at x equal -5? Well, we need to plug in -5 at both of those expressions and set them equal. I did that. How do you make sure that it's differentiable at x equal -5? Well, an argument here is you might have to go back to limits like a left-hand and a right-hand derivative. But in this case, we take the derivative of the left-hand side, the derivative of the right-hand side, and set them equal. And by the way, this has a nice, I think, a couple of really nice real-world applications. One that I'm thinking about has to do with a train track. So we, of course, want a train track to be continuous, but you also want it to be differentiable here at these places where they sort of change direction. So they have to be nice and smooth in here. And this is actually, they actually use this theory when they build train tracks, which is kind of neat. So, all right, I took the left-hand, the right-hand derivative, set those equal, and okay, kind of bluntly, this is 2 equations and 2 unknowns. So I ought to be able to solve that, and I did. I found a value for A and a value for H here. And whoops, I'm sorry. And I think, graphed it with those values of A and H, and it does look, of course, continuous and differentiable at x equal -5. That's a good problem. Try that one tomorrow morning at 8 o'clock with your students. This was a good one too. The graph of a function f is shown here. And the original problem was to find the limit as x goes to 0 of f of 1 minus x squared. So this is a limit question. Here's the way that I would do this one. I like to do this one with a change of variables. So what happens as x goes to 0? Let's see. What happens as x goes to 0? I'm going to look at this expression, the argument of f, excuse me. As x goes to 0, this expression right here is going to 1, but I have to think about how. Well, as x is getting smaller and smaller to 0, x squared is getting smaller and smaller, but I'm subtracting off a small positive number. So that expression is going to 1, but from the left. So I'm going to make a change of variables here. This is equivalent to saying the limit as t goes to 1 from the left of f of t. Now I'm going to look at my graph. T is approaching 1 from the left. What is this graph? What is this function doing? It's getting closer and closer to 3. Remember, not what is the value at 1, but what is it zeroing in on? It may not ever get there, but what is it zeroing in on? And if you like these types of problems, I'd suggest that you try these two tomorrow morning, also at 8 o'clock. Use the same function f and try to find those two limits. And again, as Curtis said, we'll post these tomorrow morning. And here's one last one for you to look at. I thought, whoops, I'm sorry, Curtis. I thought this was a very nice problem. F is a differentiable function. We know that f of 3 is 8. We know that f prime of 3 is equal to 5. Which of the following statements could be false? Oh, that's kind of a weird one. This has 5 possibilities. We know that on the AP calculus exam now, there are only 4 on the multiple choice, but this is a really nice problem. So the limit as x goes to 3 of f of x is equal to 8. Well, let's see. We know that f is differentiable at x equal 3, so we know it's continuous at x equal 3. So that means in order to evaluate this limit, we can use direct substitution. So that's got to be true. Well, if the overall limit is 8, then the two one-sided limits at x equal to 3 have to be equal, and indeed have to be equal to 8. And this is a really nice way to sort of end tonight, Curtis, because we've come full circle. Look at this expression. That's a difference quotient with that limit out there. This is actually the definition of a derivative, the derivative of that function at 3. And we know that value, it's given to us. So that has to be 5. When are we going to run across this expression that could be false? In D, this is again a difference quotient, which we've been talking about tonight, and again is a definition of the derivative, and we know that's 5 that was given to us. So, son of a gun, it's got to be E, but boy, this is a tough problem, I think. This is hard to see, hard to visualize. The limit as x goes to 3 of f prime of x is equal to 5. Well, remember from looking up above, we were told that f prime of 3 was equal to 5. And so it looks like it ought to be true. But the problem here is we can't use direct substitution to evaluate this limit. And the reason is that we don't know whether or not f prime is continuous. And if you think about that for a minute, you say, how could that be? We've got f that's a continuous function. It's differentiable at 3. How could we possibly have a function that has a derivative there, but isn't continuous there? It turns out that this is the expression that could be false. And we'll leave this as sort of an open question for tonight, too, for you to investigate tomorrow with your students. If I could arrow up just a little bit, there we go. This is sort of a classic example. Here's a function that can be different. There are functions that can be differentiable, but not continuously differentiable. So we can have a function that is continuous at a specific value, but not differentiable there. And so here's a function that you might investigate tomorrow that is continuous, believe it or not, at x equals 0. that is differentiable at x equals 0, but its derivative is not continuous at x equals 0. That's kind of cool. Great. Thanks, Curtis. Good problems for tonight.
Yeah, those were some great problems tonight. Steve, you did a
Stuff on
good job.
Facebook.
Yeah, you did a good job picking those from the Facebook group. Couple of things just to kind of clean up at the end of the evening. First of all, we'll have another session just like this one here in about 2 weeks. Steve and Tom and I will have just done a pre-calculus session the Thursday before. We're heading off to NCTM next week to do that in Washington, D.C. And then we'll turn right around and Tom and I'll still be there for the NCSM conference. And so we'll be doing this from Washington, D.C. next in 2 weeks. Tomorrow morning, I should have the teacher documents up, and the student documents will be coming closely thereafter for that
30th,
October 30th session. So be looking for those. That link will be out there. And then finally, if you have not seen it, I dropped my email address there in the chat just a moment ago. If you are a teacher looking for professional development hours, certainly reach out to me, curtis@ti.com, and I will be happy to send you that link. Thank you all for joining us this evening, and we will catch you on the next one in 2 weeks.